So now let's talk a little bit about R squared. Now remember, R squared is a measure of global fit. It's how well our overall equation in multiple regression fits the data. It doesn't tell us anything about a particular hypothesis, right? So we can't use R squared except when we're looking at incremental differences, and we'll talk about that, right? But we can't use R squared by itself as an indication of a particular hypothesis being supported. What this global fit measure tells us is that our model is okay to draw inferences from. And then those inferences are the local fit questions that answer the hypotheses. This is a global fit question. Does our model work for the data? Can we use it to draw inferences from? Not what are the specific inferences. The only exception to that is when we add additional predictors in that stepwise hierarchical linear modeling. When we stepwise add additional predictors and we see a change in R squared, then that change in R squared will tell us that the second model is more predictive, more useful, more explanatory than the first model. So this is the only case when we use R squared to support a particular hypothesis. And the hypothesis with a delta R squared is that a particular addition or change in the model, a change in the overall model, provides more explanatory power. It's incrementally better than the model that it was there before. Therefore, that additional variable is valuable. It still doesn't tell us about any particular relationship other than just the addition itself was variable. But let's talk about how R squared is calculated. So let's start with a correlation table. Right, and so we do a correlation table and we have variables x1, x2, and y. Right, and these are our two predictor variables, and then this is our outcome variable. And of course in a correlation table we have the variables down one side, and then we also have them across the top. And now we'll often see in publications, we'll just see, 1 is x1, 2 is x2, 3 is y, and then it'll just say 1, 2, 3, and they may not have these additional labels on there, but we're going to use them today. So correlation between x1 and x1, always 1. Correlation between x2 and x2, always 1. Correlation between y and y, 1. Right? Correlation with a variable with itself, always going to be 1. Generically, we refer to the relationship, the correlation between x1 and x2 as R, 1, 2. And the correlation between x1 and y as R, y, 1. And then we'll generically refer to the correlation between x2 and y as R, y2. So in our model that we're going to be using here, we have two predictor variables and one outcome variable, or three variables overall. Therefore, we have three unique relationships that we're going to measure. Now, technically, there's another side, the upper triangle here, that is also filled in this table, right? But this is exactly the same number. It's an exact mirror here. So the correlation between x1 and x2 is also the same thing as the relationship between x2 and x1, right? And same thing over here. This is R2y, and this is R1y. Because this is an exact mirror, we typically don't use that upper half, and we just leave it blank. Let's get rid of these circles too, just for the sake of efficiency, or neatness rather. And then, because these are always 1, this is called the diagonal. Here we always have 1s on the diagonal in a correlation table. A lot of times we don't put those up there. So we might put 1s, we might put dashes, or what we often see is some measure of the reliability of x1, the reliability of x2, x1, x2, and the reliability of y, of each of these variables, right? And this reliability would typically be Cohen's alpha, that measure of reliability. Not really have to worry about it now, but just be aware that these are some of the different things that we'll see on this diagonal, right? And that's our generic correlation table. So what I really want you to get here in this moment is that when I say R12, I'm talking about the correlation, the relationship, standardized relationship between variable x1 and x2. When I say ry1, I'm talking about the correlation between our x1 and y. And when I say ry2, I'm talking about x2 and y. And those are our three relationships of interest. So then from these, even without doing the regression equation, from these in the regression analysis, I can calculate r squared for the entire model. So let's do that real quick. Now I'm going to show you an equation, and I'm not going to provide any proof for it because frankly it would take a long time and be a little difficult to explain and nobody cares. So I'm just going to posit without proof this equation. R squared for the relationship among y, x1, and x2 is equal to r squared, r for the relationship between x1 and y squared plus r, the Pearson's correlation between y and x2 squared, minus 2 times r y1 times r y2 times r12. And I'm going to put that all over 1 minus r12 squared. So 1 minus the relationship among the predictors squared. You're never going to calculate it this way. Just know that this is where it comes from. This will simplify to, so this is how we do it when we just have a correlation table, which we never had just a correlation table. If we have betas, right, if we have standardized regression coefficients, then this simplifies to the sum of beta times r for each of our variables. So for instance, in this regression equation with two variables, it's beta for y and 1, that partials out 2, times r y1, right? So this is the beta is the standardized regression coefficient for the x1. Beta y1 2 is the standardized regression coefficient for the x1 variable. And then r is the correlation between that x1 variable and y. So that plus the standardized regression coefficient for the x2 variable, which we say beta for the relationship between y and x2, partialing out the relationship with y and 1, plus r y2, right? And so what I want you to get here is that this is the sum of all of the betas times their respective r's, right? So r, the relationship between x1 and y, and the beta that goes with that. This little 2 here just indicates that that this beta is not the same as this r, right? And then r, right, this is a times, if that's not clear. R for the correlation between y and x2 times the beta that goes with x2. Add that all up, it's basically the beta, the standardized regression coefficient for each of our predictors times its respective correlation between that predictor and y. And this overall, again, gives us r squared, which is our overall predictive ability of the equation.